Okay, so I wanted to kick things off with integration by parts. We're familiar with this formula that we're presented with in our Calc 2 course, and I don't know if you guys ever saw where it came from, but it's derived from exploiting the product rule. So if we have two functions, u of x and v of x, if we differentiate with respect to x, and we get the product rule, so u prime of x, v of x, plus u of x, v prime of x. And we go ahead and integrate both sides. So with respect to x. So if we integrate both sides with respect to x, well, if we initially differentiated these two functions and then we integrate them, we just get back those two functions. And then we get on the right-hand side, we get the integral of u prime of x dx dx plus the integral of u of x v prime of x dx. And we can go ahead and use Leibniz's notation, and we could rewrite the d prime of x as a du over dx. And the dx's cancel, and if we use the same method over here, we can rewrite everything as dx. Same thing as u of x, v of x, equals the integral of v of x du plus the integral of, well, this is dv over dx. We get u dv. And now if we just get rid of the function notation and rearrange, we get the integral of u dv is equal to u v minus the integral of v du. Right. Okay, so we'll start things off with a simple integral of x sine of x dx. And how we were taught initially using this formula is that we have to pick what function is going to be our u and what function is going to act as our dv. So the way we were told is we set our u equal to the function who is preferably differentiates to 0 over and over again. So if we differentiate x over and over and over again, eventually it's going to go to 0, in this case only after 2 times. So we set u equal to x, and we go ahead and set dv equal to sine of x dx. And if we follow the procedure, we have u equals x, and we have dv set to sine of x dx. Okay, we know u. Let's find v. We could integrate both sides and find that v equals the integral of sine of x dx. The integral of sine of x dx is negative cosine of x, right? And so now we have u, and now we have v, and we also need to figure out what du is. Well, if we differentiate u with respect to x, that's just 1, right? So du equals dx, right? And now we could go ahead and set up the formula, is that this integral that we're calling I, call it I is equal to u times v, so x, negative x cosine x, minus the integral of v, which is negative cosine of x, du dx. So when we go ahead and finish it up, we get that this integral is equal to negative x cosine of x minus the integral of negative cosine of x is, well, it's negative sine x. And we get a final answer of negative x cosine of x plus sine of x plus c. Okay, why did we review this? You know this. The reason we reviewed this is because I hear many of you don't know of or refuse to use tabular integration, or the DI method. And that's very unfortunate, because when solving more difficult integrals, where you have to perform integration by parts like this multiple and multiple times, it takes a lot of work and is very tedious. And there's more opportunities for you to have made small errors. Versus when you use tabular integration, it's not even a competition. It can save, by the time, if you have to perform integration by parts like 5 times, versus your opponent is using the DI method, they would have gotten the solution by the time you're not even halfway done with your integration by parts. So the DI method, it looks like this, and it's a simple pattern, and it's exploiting the integration by parts into kind of like a cheat code, and it looks like this. We make a little 2 columns, one for differentiation and one for integration. So the differentiation is what term are we setting equal to u, and the I is what term are we integrating, the function in the dv. So in this case, we would have set d equal to x, and the function we're integrating was sine of x. And the DI method works like this. We differentiate x until it goes to 0, or whatever function we have here, until it goes to 0. So when we differentiate x, we get 1. Differentiate again, we get 0. And when we integrate sine of x, we get negative cosine of x. When we integrate it again, we get negative sine of x. So we differentiate the function until it goes to 0, and then we integrate it as many times as we need to make sure that each row is full, right? If we stopped here, we're missing another term in this row. We have to make sure that each row is fully complete, and then we simply multiply these 2 terms, and then we multiply these 2 terms, and we add them together. Well, when we multiply these 2 terms, we get minus x cosine of x. And when we multiply these 2 terms, we get minus sine of x. And if we look closely, what we just did without the, more rigorous approach is we solved for our uv, right? This term is our uv, and this term is our integral of v du. Integral of v du. And we see that we have to subtract the integral of v du. So to make sure it's consistent, we add a negative sign over here when we multiply the 2. That way we get exactly the same solution. And we now see a pattern that emerges. We just arrived at the solution much, much quicker. And the process, you could see the power of this already. If we have the integral of x to the fifth or something like that, where we have to differentiate, do integration by parts like multiple and multiple times, we can just redo this pattern multiple times until we arrive at the solution, and just multiply the terms together and then add a plus c, and then we're done. So you can see the power of this, and we're gonna go ahead and for the rest of all the integration by part integrals that we come across, this is the method that we're going to be using. Okay, so I went ahead and made it a little harder, that way you can see the power of the DI method. I didn't want to go too crazy. I made it an x squared. You can make it an x cubed, an x fourth, x to the fifth. You would have to perform integration by parts 2, 3, 4, 5 times. You'd have to do this over and over again until you arrive at your solution. Well, if we know the pattern and we use the DI method, well, we're differentiating x squared, and we're integrating sine of x. And if we go ahead and look, we differentiate until 0, right? 2x, 2, 0. And then we integrate until each row has its complement. So the integral of sine of x is negative cosine of x. And then the integral of negative cosine of x is negative sine of x. And then the integral again is going to be cosine of x, right? So we know that when we multiply these two terms, it's going to be our first u times v, and then we have to subtract the integral of v du. Well, v du is when I multiply these two terms, so I have to subtract them. So I could just do that by adding a negative sign over here. And then I would have to repeat the process all over again, right? I have to do integration by parts twice. This was the first integration by parts, and then these two rows correspond to the second integration by parts. And so I would just have to add a negative sign over here, right? So there's the pattern. When I make my DI columns, the pattern is this term is positive, this term is negative, this term is positive, this term is negative. So every time we write the DI, we're going to automatically put in the plus minus, plus minus, plus minus as many times as we need. That way we don't get confused. And all we have to do is multiply these two terms together, add them to the product of these two, and then add them to the product of these two. And what do we get? We'll check for yourself. Negative x squared cosine of x. Minus minus makes a plus, so plus 2x sine of x. And then plus 2 cosine of x plus c. And would you look at that? Exactly the same solution. So now we're going to go ahead and take a look at a few problems where neither term differentiates the zero, so both functions would be infinitely differentiable. So let's go ahead and take how we would do the DI method for those integrals. Okay, so we're given the integral of e to the x cosine of x. So now no longer does one of the terms differentiates to 0. So what term do we pick to differentiate? Most of the time, it's the one that's easiest to differentiate. And I'll go ahead and make a little video on, when and how you know which term to set to u and dv. But for now, we're going to go ahead and say, well, the exponential is always going to be the easier to differentiate. It's just itself, right? So we set d equal to the exponential, and I, the integration to cosine. And, well, if this doesn't differentiate to 0, how many times do we need to differentiate it? This is where you have to understand the pattern, right? Beforehand, all we had to do was differentiate until it goes to 0, and then multiply the products in this pattern that we figured out, right? So when you perform integration by parts, you see that you have to apply differentiate by parts 2 times. That way we yield the same integral that we initially started with, as you remember in your Calc 2 course. That way we can say, okay, if I equals integral of e to the x cosine x, and after performing integration by parts twice, out pops out I. And we could just go ahead and solve for I, and we get our solution. So the goal was to perform integration by parts until we arrive at the same function we started with. That means we want to integrate it until we get back to the same function. In this case, it's cosine of x. So let's go ahead and integrate cosine of x until we arrive back at cosine of x. So the integral of cosine, well, that's just sine. Integral of sine is negative cosine, right? So now we're done. We just have to make sure each row is full. So all we have to do is differentiate e to the x twice. It's just e to the x, e to the x. And now we could go ahead and do that pattern again. Plus minus, plus minus. And we go ahead and multiply these two terms together. Then we multiply these two terms together. But now what do we do? Well, look. Notice if we multiply these two terms together, we arrive at the I we initially started with. And that was the whole point of the integration by parts, was to arrive back at this e to the x cosine of x. So to finally get our solution, now we just have to multiply these two terms together, and this is the integral that we're left with, right? This is going to be our I. So we can say that I equals, okay, we know the first two terms. It's e to the x sine x. And then it's minus makes plus, so plus e to the x cosine x. And then we get minus I. Just like we got over here, go ahead and solve for I. And we get the same solution, right? Yeah. That's the power of tabular integration. And we're going to go ahead and solve some progressively more trickier and trickier problems. That way you get a hang of it. And you'll see that it's an indispensable tool for integration, and not just for integration bees and integrals in their own right. You have to solve integrals everywhere in your courses. So this is going to save you a lot of time on exams and make your life a hell of a lot more easier. Some people say that mathematicians are lazy. This could, you can make an argument for that, but it's more about efficiency, right? Because if I can make my life easier computing something, I'm gonna make my life easier. So it may seem very, unintuitive or a bit uneasy when first seeing the DI method, but when you break the problem apart for yourself using natural integration by parts, and then you compare it to the DI method. That way you get the ins and outs of what's happening. Because I know I went very pretty quickly, right? um, then you build this new muscle for it, and then you come to realize, wow, I'll easily outperform anybody who doesn't use the method anymore, right? So, and obviously that's very important to you uh, if you want to solve tough integrals in a short amount of time, especially if you're competing against others. So let's go ahead and see what lies ahead.